Okay, C13 nuclear magnetic resonance spectroscopy. This technique is very useful to distinguish different carbon atoms present in a molecule. Okay, C13 NMR, the principles, right? Most of the principles are exactly same like proton NMR, right? We are going to focus on some of the important concepts which are very useful for the competitive examination, like PGTRB or CSA or JRF net, like that. So I am not going to discuss the complete principles because I have given some enough idea about the nuclear magnetic resonance in proton NMR itself. So I am not going to discuss once again the complete principles here, but I am going to discuss the basic ideas, okay, which are very useful for competitive examinations. Okay, so let's proceed. Right. So if you come to C13 NMR, this is a very useful technique by which you can find the different carbon atoms, chemically non-equivalent carbon atom, or we can say the other way, magnetically non-equivalent carbon atoms can be distinguished using this technique. Okay, right, listen. So C13 NMR is all about the carbon atom. You all know that carbon atom has three different types of isotopes: C12, C13 and C14. For C12, the spin quantum number is 0, which means C12 nucleus does not have the property of spin. Okay, so it is inactive, right? It is inactive in NMR. So C12 is not important for us. What about C13? For C13, the nuclear spin quantum number is half. It is NMR active nucleus. Okay, it is NMR active, right? So this is very important for us. We are going to focus on C13 only. What about C14? C14 is radioactive element, radioactive. So we are not going to discuss about C14 isotopes here. So in C13, out of 3 isotopes, the C13 isotope has I value half and it is NMR active. So we are going to focus on C13 nucleus here. Okay. Now, if you compare the natural abundance, right? You know very well, hydrogen atom exists as proton, deuterium and tritium. The natural abundance of proton is 99.98, extremely high. Okay, it's very high. It has very high natural abundance. So the proton NMR spectrum is usually gives intense signals compared to C13. Proton NMR will give intense signals. What about C13? Listen, this is our focus now. For C13 nucleus, the natural abundance is just 1.1%, or I can say roughly 1%. C13 is just 1%, whereas proton is 99.98%, almost 100. But C13 is 1.1% abundance. Okay, and here I have given the natural abundance of few more nucleus. For F19 and P31, natural abundance is 100. What does this indicate? This indicate these values, 100% natural abundance indicates that the F19 and P31 may not have isotopes, right? Or even if they have isotopes, their natural abundance is negligibly small. Okay, so that's the point. Then another important information which is very, very important for us, gyromagnetic ratio. Okay, I have given the value in 10 power 7 radians per Tesla per second. This is the unit of gyromagnetic ratio, radians per Tesla per second. For proton nucleus, the gyromagnetic ratio gamma is 26.75 into 10 to the power 7 radians per Tesla per second. For C13 nucleus, gyromagnetic ratio gamma equal to 6.73 into 10 to the power 7 radians per Tesla per second. Like that, for F19, P31 I have given here, you just go through that. And observe carefully, I am going to compare these two because in organic chemistry, yes, most organic chemists, they use either proton NMR spectrum or C13 NMR spectrum. F19, P31 are rarely used by organic chemists, but F19, P13 also very important, which will give information about the structure of the molecule, right? But F19, P13 are very important for inorganic studies, right? Generally, organic chemists prefer these two, right? Now, here, if you observe this carefully, if you compare the gamma value of proton and the gamma value of C13, see, don't worry about 10 power 7, just compare these values. 26.75, 6.73, it is approximately 4 times, right? So, gamma value of C13 is 4 times smaller than the gamma value of proton. Okay, gamma value will give you the idea about the energy gap. Okay, see, you all know that see the energy gap between the alpha state and beta state. See, in the case of proton nucleus, in the case of proton NMR, the gap between the alpha state and beta state, okay, the gap is large. Why the gap is large? Because the energy gap is equal to it is gamma into H cross into the magnetic field strength. Okay. Now, if I apply same magnetic field for proton nucleus and C13 nucleus, if I apply same magnetic field, then the gap depends on the value of gamma. In the case of proton nucleus, gamma value is large, so this gap also large. Whereas in the case of C13 nucleus, what happens is that even if I apply same magnetic field, since gamma value is small for C13, the gap between the alpha state and beta state reduced. It becomes small. Okay. If the gap is small, then the population difference between the alpha state and beta state, the population difference becomes very, very, very small. If difference in population become very small, then it is very difficult to detect the signal. Okay. Whereas in proton NMR, the gap is somewhat large. So population in the alpha state is somewhat greater. So the difference in population is somewhat greater. So we can get the signal. We can get somewhat good signal for proton NMR. Whereas in C13, since the gap is small, the population in the alpha state is very, 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 very small. Or I can say alpha state, beta state have almost close population, equal population, almost. So difference is very small. Since difference in population is very small, it is very difficult to observe signal in C13 NMR. Okay, so this is very important. Keep this in mind. Right, gamma value decides the gap. Okay, keep that in mind. Not only gamma value, even the magnetic field strength. If I apply same magnetic field strength for C13 and proton, then gamma value of proton is large, therefore the energy gap is large. If energy gap is large, then population difference also large. If population difference is large, we get intense signal in the NMR spectrum. Okay? Listen, what is the standard reference we use in NMR? C13 NMR. Listen, like proton NMR, even for C13 NMR, we use the same standard tetramethylsilane. Okay, silicon atom in which 4 methyl groups are directly connected. Okay, this is called tetramethylsilane. We use tetramethylsilane as the reference compound even for C13 NMR. Okay, then the chemical shift. Yes, this is very important. Listen, in the case of proton NMR, the chemical shift range is from 0 to roughly 15 ppm. 0 to 15. Okay, whereas for C13, the chemical shift range is large, 0 to 220 ppm. It's very large. Okay, keep this point in mind, very, very important. And there are exceptions also here. Here there are 2 exceptions. Now keep this in mind. The exception 1 is methane. For methane, chemical shift value is actually negative. Okay, let me give the value for methane. The chemical shift value is in the case of methane, the chemical shift of the carbon appear in the value of minus 2.5 ppm. It is negative. And number 2, negative means it appears beyond TMS. That's the meaning. Right? And second one, carbocations. Listen, carbocations. Right? This carbocation carbon appear with the chemical shift of 334 ppm. Very, very high. Very, very high. Okay. So these 2 are exceptions. Apart from these 2, all other carbons present in any molecule they will appear in the range of 0 to 220 ppm. Okay, keep this in mind. The next point is that isotopomers. Isotopomers. What are isotopomers? Listen, 2 compounds, they have same molecular formula, same structure, everything same, except their isotopes. Okay, one isotope or one or more isotopes of one molecule and the other molecule may be different. Okay, those molecules which differ by isotopes are called isotopomers. For example, see, I'll take carbon tetrachloride, in which the carbon atom is a C12 carbon atom. Now, I'll take another molecule, CCl4. This is also CCl4, same molecular formula, same structure, everything. But now, this carbon is not C12 carbon, it is C13 carbon. Okay, so these 2 compounds, both compound have molecular formula CCl4. Okay, structure tetrahedral, this is also tetrahedral, everything same. What is the difference? In this molecule, the carbon atom has C12 isotope, and in this molecule, the carbon atom has C13 isotope. So, the difference is only on isotopes, isotopic atoms. So, these 2 are called isotopomers. Okay. Is this clear to all? Are you able to follow? I have told you the chemical shift range for C13 is 0 to 220 ppm. Generally 0 to, this is the overall range. Chemical shift range, right? It is 0 to 220 ppm generally for C13 NMR. Now, if you get signal between 150 to 220, observe carefully. If you get signal between 150 to 220, then it should be a carbonyl group. It should be a carbon atom of the carbonyl group. Carbon atom of the carbonyl group appear in this range from 150 to 220. Remember, above 150, if you get a signal, that signal is due to carbonyl carbon. Now, in carbonyl, see, what are the compounds of carbonyl group? It may be a aldehyde, it may be a ketone, it may be carboxylic acid where we have carbonyl group, and acid chlorides, then we have esters, then we have acid anhydrides, and we have esters, then we also have amides. All these compounds, they have carbonyl carbon. All these carbonyl carbon appear in the range of 150 to 220 in the C13 NMR spectrum. Okay, now listen, in the case of aldehyde, right, aldehydes and ketones, see, aldehydes and ketones, they appear from 191 to 208. Observe carefully. If you get a signal, right, between 191 to 208, it should be either aldehyde or ketone. Very simple. It should be either aldehyde or ketone. Listen, it is very difficult to distinguish aldehyde and ketones. Generally, it is difficult to distinguish aldehydes and ketones through C13. Okay, somewhat tough, but using proton NMR we can distinguish. Okay, anyway. Right, we'll discuss about broadband decoupling, off-resonance decoupling as we go along. Right, I'm just giving you from the C13 NMR spectrum of point of view. Okay, now, so for aldehydes and ketones, we get signal from 191 to 298 ppm. Between this, you'll get a signal. Then the carbon atom of the carboxylic acid, carbon atom of the acid chloride, carbon atom of the acid anhydride, esters, amides, these carbons will appear in the range of 164 to 180 ppm. Okay. In this range, if you get a signal, it may be carbon atom of carboxylic, it may be carboxylic acid, it may be acid halide, it may be anhydride, it may be ester, or it may be an amide. Observe this carefully, very important. Using C13 NMR, we cannot distinguish. It's a very, very important point. Identifying acid derivatives by C13 NMR is difficult. Let me write here. See, identifying acid derivatives. Acid as well as acid derivatives, right, by C13 NMR is difficult. It is difficult. Okay, it's very, very, very tough task, right? So, if I get a signal between 164 to 180, I can say that a carbon atom of the acid derivative, any of these acid derivative may exist. Okay, if I get a signal between 190 to 298, it is carbon atom of the carbonyl group carbon of aldehyde or ketone. We can very easily say that. Okay, done. Listen, see, I have told you the natural abundance of C13. Natural abundance of C13, I have given 1.1. Let me take roughly 1%. What does this indicate? See, suppose if we have a molecule, say methane. Okay. Listen, if I take, for example, if I take an ensemble of methane. Okay. Meaning I am taking some collection of methane molecules, say 100 molecules. Say 100 molecules. Listen, since the natural abundance is only 1%, which means out of 100 molecule, one molecule may contain C13 nucleus. Out of 100 molecule, one molecule may contain. I cannot exactly say that yes, one molecule must contain C13. No. Out of 100, okay, one molecule may contain C13 carbon. Are you able to follow? So, the remaining 99 molecule, even if you keep them in a magnetic field and if you pass radio frequency radiation, nothing will happen. Because in other molecule, the carbon nucleus is C12. C12 is inactive. So, to get the spectrum of C13, you need to scan for more time. Okay, so C13 NMR usually requires a huge time to take the spectrum compared to proton NMR. Okay, the reason is, if you take 100 molecule out of 100 molecule, or one out of 100 molecule may contain C13 nucleus. Only that molecule is active. So if you want to take some intense, or if you want to take a good spectrum, you need to take large amount of sample. So this is one of the limitation. We need large amount of sample compared to proton NMR. Okay, compared to proton NMR, in C13 NMR we need large amount of sample because the abundance is very, very low. Okay, so the sensitivity of C13 signal is generally poor. Okay, yes, keep that point in mind. This is very, very important. It's an important point. Listen, see the sensitivity of the signal. Sensitivity of signal, it is directly proportional to gamma power 3, gamma cube, and it is also proportional to natural abundance. Okay, see, if you compare the proton NMR and C13 NMR, right? Listen, in the case of C13, if you compare C13 gamma value with the proton gamma value, the C13 gamma value is very, very less. So I can say that the intensity of the proton NMR signal, see, observe carefully, intensity of the proton NMR signal, right, it is approximately equal to, listen, if you compare gamma value of proton and gamma value of C13, gamma value of proton is 4 times greater than the gamma value of C13. Okay, so since it is 4 times greater, right, so gamma value is 4 times greater than C13, so I'll put 4 into 4 into 4 because I have gamma cube here. And natural abundance is, in the case of proton NMR, the natural abundance is 99.9, almost 100. Well, this is just 1%. So, proton NMR is 100 times greater than the natural abundance of C13. Okay, so this is intensity of the C13 NMR signal. I'm just comparing the intensities. Now listen, if I multiply these, I'll get 6,400 times more intense than the C13 NMR signal. Observe carefully, it's a very important point. Proton NMR, intensity of the proton NMR, sensitivity of the proton NMR signal is 6,400 times larger than C13. So C13 NMR signal, okay, the sensitivity is very, very, very less. Right? Keep this in mind, very important. Right? So I have given the chemical shift values of the carbonyl group which appear between 150 to 220. What about the remaining? Okay, let me give the values. Next page. Yeah. Remaining values. This is very important. Isn't it? Chemical shift range from 100 to 150, this range. Beyond 150 we have told you. Now 100 to 150. 100 to 150, okay, will give information about carbon-carbon double bond. That is carbon atom present in doubly bonded carbon and carbon atom present in aromatic carbon. Because here also we have double bond, so carbon atom of the double bond and carbon atom of the alkene, carbon atom of the benzene will usually appear in the range of 100 to 150. 150. Keep this in mind. If I get a signal between 100 to 150, it is probably due to carbon atom of alkene or carbon atom of an aromatic ring. Okay. Then next one, the chemical shift value from 0 to 100. If you value 0 to 100. In this is very important. Listen, from 0 to 50, we give the value here. From 0 to 50 ppm, right, usually sp3 carbon exists. sp3 carbon exists from 0 to 50. Then 50 to 100, we have carbon-carbon, triple bond carbon atom of the triple bond, then carbon atom of single bond oxygen CO, carbon atom of the CO bond, where we have single bond between carbon and oxygen, right? Then from roughly 25 to 75 ppm, we have carbon atom connected to nitrogen, carbon atom single bonded nitrogen, carbon atom connected to chlorine, carbon atom connected to bromine. These carbons usually appear from 25 to 75 ppm. Okay, these are all some usual range for different compounds. Okay, keep this in mind. Okay, so number of signals. How many signals we get? Number of signals is equal to, right, number of non-equivalent carbon atoms present in the molecule. Okay, it depends on number of non-equivalent carbon atoms, right? Magnetically non-equivalent. Very specifically saying magnetically non-equivalent. Remember, if two nucleus are chemically non-equivalent, it should be magnetically non-equivalent. But if two nuclei are chemically equivalent, then the two nucleus may be magnetically equivalent, magnetically non-equivalent. Okay, this is a very important point. We'll discuss about that as we go on. Now, so I have given this point, keep this in mind. Number of signals is equal to number of magnetically non-equivalent carbon. Okay, let me use that word so that you will get some clarity. Number of magnetically non-equivalent carbon atoms present in the molecule. Okay, now I'll give some examples. Okay, you try to tell me how many signals we get for each of these for the following compounds. Okay, yeah. So let me give few questions. See, here I have given few questions. You try to tell me how many signals we get for these compounds in C13 NMR spectrum. Isn't? See, symmetry principles are very useful to decide to find number of equivalent carbon atoms. See, here in methane molecule we have only one carbon, so we can directly say that it will give only one signal in the spectrum. Very easy. Whereas in ethane, see, if I put a plane here, right? Yes, in either side of plane we have same unit, right? Methyl, this also methyl. So that means this carbon and this carbon, they are equivalent. So we get only one signal for ethane. Number of carbon is 2, but we get only one signal. Okay, then if I come here, in this molecule, see, if I keep a plane here, K plane or axis, whatever it is. See, either side of the plane, okay, I have a CH3 group here and CH3 group here, they are equivalent. So that means if this is carbon A and this is also A, because they are equivalent, and the middle one is B. So this will give two signals. A carbon atom will give one signal, B will give another signal. So we get two signals. For benzene, all the 6 carbon atoms are equivalent. So we get only one signal. And for these species, listen, I have given these species, right, just for making you to understand. Just by drawing chlorine here or here, sometimes we may think that this is chlorobenzene, this is orthochloro. Observe carefully. You are all MSc, so you know the difference, but keep this point in mind. All these compounds are one and the same. I have drawn in a different direction, that's all. So here, the chlorine attached carbon, right, it is in different environment, which is A. Then the next carbon, orthocarbon, B. Next metacarbons are equivalent, C. Then paracarbon, D. So we get 4 signal for this compound. Okay. And listen, these are all one and the same. I have drawn in a different direction. Okay. Yes, just for making you to understand this, I have given this point. Then this is orthodichlorobenzene. In orthodichlorobenzene, see, I can keep a plane here. If I keep a plane here, that plane divides the molecule into 2. Now see here, I have one carbon here, another carbon here, another carbon here. So we have 3 carbon. So we get 3 signals. We get 3 signals in the C13 NMR spectrum. Okay, what about here? If we keep a plane here, okay, we can divide the molecule into 2 equal half. And now listen, if I count from this direction, listen, this is carbon 1. Even carbon atom passing through the plane should be counted. So here I have 1 carbon, here 2, 3 and 4. Yes, we get 4 signals in the C13 NMR spectrum. What about here? Yes, we can divide this molecule, or we can keep 2 planes here, one passing through chlorine, another one passing perpendicular to the line connecting the 2 chlorine. Okay. Now, since it has 2 planes like this, we can count number of carbon between the 2 planes. Okay. So between this plane and this plane, how many carbon atoms are there? Here I have 1, and another, see, along this plane, we have second carbon, so 2. So this molecule will give 2 signals in the C13 NMR spectrum. Okay. Let's try to find the number of signals that we get in the C13 NMR spectrum of these compounds. Listen, how to work it out, very simple. Use symmetry ideas. Use plane of symmetry or axis of symmetry. Okay, you can easily identify this. Listen, so naphthalene is a planar molecule. So you keep a plane here passing through this carbon-carbon bond, and keep another plane passing through the centers of this and this. Okay. Listen, you have to keep as many planes that is possible in the molecule. As many planes as possible. Okay. In naphthalene, these 2 are the planes which passes through the molecule. And another plane is there which is passes through all the atoms. We are not considering that. Okay. To identify number of signals, you need not consider. You just see planes which cut the molecule in a perpendicular manner. Okay. Yeah. Now listen. Here, so we have divided this molecule using 2 planes. Now between the 2 planes, how many carbon atoms are there? You count. Between the 2 planes. Right. So in one quadrant, I can say another way. Isn't so here, see, this carbon is passing through this plane, so you have to count it 1. Then we have 2 here, and we have one more carbon 3. So between this plane and this plane, we have 3 carbon atom. Yes, naphthalene will give 3 signals in the NMR spectrum. C13 NMR. What about anthracene? In anthracene also similar, listen, a plane passing through these 2 carbon, this carbon and this carbon, and we have another plane passing through the centers like this. Now, you take this plane and this plane, between these 2, how many carbon atoms are there, you see. Because in one quadrant, whatever carbon atoms present here, right, in the other quadrant also, similar carbons are there. They are all equivalent. Okay, so I'll just count it. So here I have carbon which is passing through the plane. So 1, here I have 2, here I have 3, and here I have 4. Yes, anthracene will give 4 signals in the NMR spectrum. Whereas in phenanthrene, see, I have a plane here. If I keep a plane here, yes, I can divide the molecule into 2 halves. But I don't have plane here. Because if I keep a plane here, see, this part is here. But in the other side, I don't have the similar part. So this molecule has only one plane. Now, listen, either you count number of carbon this side or that side, because they are equivalent. So let me count it here. So this is carbon 1, this is carbon 2, carbon 3, carbon 4, carbon 5, carbon 6 and carbon 7. Yes, we have 7 carbon atoms, okay, or 7 magnetically non-equivalent carbon atoms. So we get 7 signals in the spectrum for phenanthrene. Okay, similarly, we can find out for pyrene. This compound is called pyrene. Now we can keep a plane passing through the middle carbon atoms. Okay, this carbon and the middle 2 carbon and this carbon, we can keep a plane here, and I can have one more plane. I can place it like this. Okay, I can place it like this. Now you take, see these 2 plane cuts the molecule into 4 equal part. You take any one quadrant and count the number of carbon. So let me take this quadrant. Actually we have 4 quadrants here. Let me take this quadrant and count the planes. Okay, I am just using the word quadrant just for identification purpose. Easy to understand. Okay. Now, so how many carbon atoms are there? See, one carbon is present in the plane itself. So you have to consider that also. 1, 2, 3, 4. Okay, and we have one more carbon. See here, this carbon also should be counted. So I have 5 carbon atoms totally. So pyrene has 5 carbon atoms, 5 magnetically non-equivalent carbon atom. So it will give 5 signals in the spectrum. Okay, take note. Yeah, in this molecule, see, you can keep a plane passing through this carbon, middle 2 carbon and this carbon. Okay, you can keep a plane passing like this, so that this left hand side part, this part and this part, okay, they look alike. See, so we have divided the molecule into 2 equal half, right? And there is no other plane here. So what I am going to do, I am going to count the number of carbon atoms from any one of the side, this side or that side. Okay, let me count in this side. See here, 1. Here I have 1 carbon. This is passing through the plane, so you should count it. 1, 2, 3, 4, 5, 6, 7, 8, and middle we have 2, okay, because the plane is passing through that carbon also. 9 and 10. Yes, this compound will give 10 signals in the C13 NMR spectrum. Okay, take note. See this example. Suppose if we keep a plane here, see, I have bromine atom attached to this carbon, but exactly in the other side, I don't have bromine here, but instead bromine is present in the next carbon. So this molecule does not contain this plane of symmetry. This plane of symmetry is absent. Okay, but the molecule has an axis of symmetry. Isn't the entire molecule is planar? So what I am going to do, I will keep a plane passing through the center like this. Center like this, right? Between, see, middle 2 carbon, you take this point and keep an axis here. Keep an axis here. Now, along this axis, rotate the molecule by 180 degree. If I rotate the molecule 180 degree, what will happen? This bromine will go there and that bromine will come here. You will get the equivalent shape. So this molecule has C2 axis. 180, no. So 360 by 180 is 2. So this axis is called C2 axis. This molecule possesses C2 axis. Okay, so using that you can rotate, right? So that I can bring this bromine to here and that bromine to here. Okay, so in this structure, this is very important to count the number of equivalent carbon atoms. Okay, how? If I rotate, what will happen? See, this carbon will go there and that carbon will come here. So this is 1. Then this carbon will go here and that carbon will come here. So this is 2. So this carbon 1, this carbon 2. While rotating, what will happen? This carbon will go there and this carbon will come here. Okay. See, this carbon will go here. So we can count 1, 2. This is 3. Here we have 1, 3. Let me write the number so it's easy. 1. Here also 1. This is 2. This is 2. This is 3. This is 3. Okay. This is 4 and this is 4. And this is 5 and this is 5. If you rotate by 180 degree, they come to the, they exchange their position. Okay. Then I'll take this is 6. This is 6. Therefore this is 6. This is 7. Therefore this is 7. Okay, if you rotate the molecule, what will happen? These two carbon also exchange their position. So if this is 8, this is also 8. If this is 8, this is also 8. If you rotate the molecule, right, the equivalent carbon, they exchange their position, they are equivalent. Okay, therefore, how many different carbon atoms are there? Chemically or magnetically non-equivalent carbon. We have totally 8. So this compound will give 8 signals, okay, in the C13 NMR spectrum. Take. For this molecule, we can also use a plane, but this plane you should carefully draw. Listen. Let me redraw the structure of the pyrene substituted compound. Aromatic. And we have a bromine here, Br, and another bromine here. Okay. Now we don't have plane of symmetry here. We don't have plane of symmetry here, but we have a plane of symmetry between this carbon and this carbon. It is passing like this. Observe carefully. We have plane of symmetry passing through this carbon and this carbon. See, this part and this part, they are exactly equivalent. Okay. But, I'm very sorry. Sorry, this molecule has only axis, so it is wrong. Right? Never worry. Okay, so based on axis, I have given you how to find the number of different carbon atoms associated. Now, let me move on to the next molecule. See, that is question number 13. Draw a line here, which is nothing but a plane, which divide the molecule into 2 equal half. And here, this is carbon 1, this is carbon 2, this is carbon 3. So, this will give 3 signals in the C13 NMR. And in this molecule, see, this side I have aromatic ring and this side I have an alicyclic ring. Okay. So, see, this carbon and this carbon are equivalent. So, if I take this is A, this is also A. And this carbon are equivalent. B and this also B. If this is C, this is also C. Similarly here, this and this are equivalent. So, if this is D, this is also D. If this is E, this is also E. Okay, so how many signals we get? A, B, C, D, E. So we get 5 signals in the C13 NMR spectrum of this compound. Okay, take it. Then we'll move on to this molecule. This is pyridine. In pyridine, yes, we can keep a plane passing through this carbon and the nitrogen. We have a plane here, which divides the molecule into 2 equal half. Now you count the number of carbon, 1, 2. And another carbon passing through the plane, you should count that also. So, pyridine molecule has 3 magnetically non-equivalent carbon. So, it will give 3 signals in the C13 NMR spectrum. Okay. Then, so this is pyridine. Then pyrrole. Yes, in pyrrole, if I keep a plane here, we can divide this molecule into 2 equal half. And we have 2 different carbon. So, this will give 2 signals in the C13 NMR. Similarly, furan also will give 2 signals in the C13 NMR. Just count the number of signals that we will get in the C13 NMR of these compounds. Listen for question number 18. Listen. This carbon, and this carbon, they are all equivalent. Okay, if I say this is A, this is also A, this is also A, this is also A. Then the bridgehead carbon, they are equivalent, so they are B. And this carbon which is at the top, this is C. So this compound will give 3 signals, right, in its NMR spectrum. C13 NMR spectrum will get 3 signals, right? And for the second one, we have 2 double bonds. So this is A, this is also A, this is A, this is also A. All these 4 are equivalent. And this is B, and the top one is C. Yes, this compound also gives 3 signals in the NMR spectrum. Now this is actually a planar molecule, so you can keep a plane here, plane passing through the middle carbons like this. We have only one plane here, and count the number of carbon. 1, 2, 3, 4, 5, and along the plane we have these two carbon. That also should count 6, 7. So this compound will give 7 signals in the C13 NMR spectrum. Okay, then next one. This compound, see here, this bridge, see these two methylene group, these two methylene, they are all equivalent. So if this is A, this is also A. This is A, this is also A. This is A, this is also A. All the 6 carbon atoms are equivalent. Whereas the bridged carbon, if this is B, this is B. They are different. So we have totally 2 different types of carbon. So we get 2 signals in the NMR spectrum. In cubane, all carbon atoms are equivalent. So we get only 1 signal for cubane. And this is called adamantane. In adamantane, CH2 carbon atoms are equivalent. See, this is A, CH2, this is CH2, this is CH2. Then this is CH2, this is CH2, this is CH2. So I have 6 CH2 carbon, they are all equivalent. Then we have methane carbon, CH carbon, CH. This is one CH, this is one CH, this is one CH, and this is one CH. I have 4 CH carbon, they are all equivalent, they will give 1 signal. So adamantane will give 2 signals in the NMR spectrum. Okay, take note. Find the number of signals that we get in the NMR spectrum of this compound. Listen, in this, we can keep an axis here, right? If I rotate by say 72 degrees, see, this carbon will come here, this carbon will come here. Okay, we can do rotation, right? Or I can place a plane here, I can place a plane here, I can place a plane here. So we can place many planes. Let me show you how to do that. Listen.
Sir?
Listen. Yes, sir. Yes.
Sir, now for symmetry of the...
See, if you use planes, it is very easy to identify. Listen. Let me keep a plane here. Observe carefully. Along this carbon-carbon double bond, I will keep a plane. This is one plane of symmetry. Then along this carbon-carbon double bond, we should keep a plane. Kindly bear with me, it's not exactly straight line, actually we should draw. Then along this carbon-carbon double bond, we should keep a plane. Observe this carefully. Then along this carbon-carbon double bond, we should keep a plane. Okay. Right, so I have, then we have one more, right, along this carbon-carbon double bond. We can place one more plane. Right. So how many planes are there? See, how many planes are there? 1. I'll start from here. This is 1, 2, 3, 4, 5 planes, correct? 1, 2, 3, 4, 5 planes. Okay, this is one plane. This is 2, 3, 4. I have 5 planes because this is my center ring is pentane. So we should have 5 planes. Now you take any 2 plane and count it number of carbon between that. Okay. So to count the number of carbon, what I am going to do, you take any 2 planes. I will take this plane and this side, and between these two, how many carbon atoms are there, you count. Very simple. See here, I have 1 carbon, 1, and this plane is passing through 2 carbon, 2 here, 3 here. Correct? Correct? That's all. Right? Between these two, I have 3 carbon atom. Similarly, between all other adjacent plane, adjacent axis, plane of axis, we have 3 carbon atoms. So this molecule will show 3 signals in its NMR spectrum. Okay, take note. Yeah, the question is how many signals we get in the C13 NMR spectrum of these 2 compounds. Let me take this as compound A, this is compound B. Yes. So you just see these 2 molecules are planar molecules, so you can use planar symmetry. If planar symmetry is not there, you can use axis. Okay. Yeah. See here, I have I can keep a plane passing through the OH attached carbons. It passes through the middle 2 carbon and the OH attached. I have a plane here. We can keep a plane like this, so that we can divide the molecule into 2 equal half. We can also keep a plane passing through the center of these 2 carbon, right? and center of these two carbon. We can keep a plane like this. So we have two planes in this molecule. Now to count the number of magnetically non-equivalent carbon, you take any two axes. Okay, suppose I'll take these two axes. I'll count the number of carbon atoms from this to this. Okay, so here I have one carbon, one. Here I have two. Here I have three, and here I have four. Okay, and see, this plane is passing through this carbon. Don't forget, between these two, if any carbon present in the plane, that should also be counted. So this is 5. So molecule A has 5 magnetically non-equivalent carbons, so we'll get 5 signals. Okay, then what about this? Yes, this compound also has plane of symmetry, but it has only one plane passing through these carbon atoms. If I keep a plane here, yes, see, we can divide the molecule into 2 equal half. Okay, now how many carbon atoms are there? Now you can count the number of carbon this side or that side, both are equivalent. Okay, so I'll count from here. So this carbon is passing through the plane, you should count it. 1, 2, 3, 4, 5, 6, 7, 8. Then see, middle we have 2 carbon, that should be counted. Okay, 9, 10. Yes, in this molecule we have 10 magnetically non-equivalent carbons. So we get 10 signals in the C13 NMR spectrum of this compound. Okay, take 2. Yes, see here I have given a question. And what we have to do is, you need to identify out of these 4, which one will give 6 signals in the C13 NMR spectrum. Out of these 4 compounds, which one will give 6 signals in the C13 NMR spectrum? Okay, yes, try to identify them. See, in molecule A, all the 3 methyl groups are attached at in equatorial position. All are in the equatorial position, and it is, if this is 1, this carbon is 2, this is 3, this is 4, this is 5. They are in 135 position. 135 position. So if I keep a center and if I keep a plane, axis passing through the center axis, and if I rotate by 120 degree, this axis is called C3 axis. If I rotate by 120 degree, this carbon will come here at C1 carbon will come to C3 place. C3 will go to C5. C5 will come to C1. So they are all equivalent. Therefore, now I'll count from this carbon to this carbon. 1 to 3. Okay, so I have 1, 2, 3, and this methyl is 4. So this will give only 4 signals in the NMR spectrum. If I rotate, alright, carbon 1 will come here. So 1 and 3 are equivalent. 4 will come here. 4 and this carbon are equivalent. Okay. And 2 will go there. So 2 and this carbon are equivalent. And 1 will come here. Right? And these 2 are equivalent. Therefore, this molecule will show only 4 signals in its NMR spectrum. Okay. Whereas if I take this molecule, see here I can keep a plane. Plane passing through, listen, passing through this carbon and the methyl carbon and this carbon. So you have to draw plane like that. You should draw carefully. The plane is passing like this. Plane is passing at the middle. Observe carefully. You divide the molecule in such a manner that you should divide this carbon, and the plane should pass us in the middle, and it should divide this carbon. Therefore, see, you will get 2 equal half. Now you count the number of carbon. 1, 2, 3, 4, methyl carbon 5, and this carbon 6. Yes, this compound will give 6 signals in its NMR spectrum. Okay, and for this molecule there are no symmetry elements present. Right? So all the carbon atoms are non-equivalent. So we get 8 signals. 8 signals. Okay. Right. So what about here? If I keep a plane passing through this carbon and this carbon, it's somewhat difficult to observe. It's somewhat difficult, but you won't get. No, there is no plane of symmetry observed. Right? If I keep a plane passing through this carbon and this carbon in this manner, if I do reflection, it will reflect to the other side. No, we won't get. So here also all the groups are different, so we'll get 8 signals. So only the second one will give 6 signals in its NMR spectrum.